Okay, welcome everybody to Astronomy Education. I think it's going to be not very well attended tonight because of the concert. But anyway, we'll press on. It is recording. My name's Colin Hill, and tonight's talk is cosmology. So what is cosmology? Well, cosmology is the study of the birth and evolution of the universe. We can compress that into about 40 minutes, okay? I'll also be talking about redshifts, forces of nature, and how the possible endings of the universe as well. Okay, so let's get started. Before I do, I'd just like to acknowledge and pay our respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country and respect and value their past, present and ongoing connection to the land and cultural beliefs. So, as I said, cosmology is the study of the birth and evolution of the universe. But it was originally thought, this was sort of before the 20th century, that the universe was static and unchanging, as it's always been there and always will be there. When Albert Einstein developed general relativity, he found that his field equations showed that the universe was actually expanding. And this sort of went against, common knowledge. Everyone thought it was static and unchanging. So he introduced a term called the cosmological constant into his field equations to produce a static universe, and everyone was happy. However, this all changed in 1929 when Edwin Hubble showed that the universe is actually expanding, exactly what the general relativity equations showed. Georges Lemaitre had suggested this 2 years earlier as well. It was later on when Albert Einstein acknowledged that the universe is actually expanding, and he had to remove the cosmological constant from his equations. He said that that was the biggest blunder of his life, putting that into his equations. Now, Hubble determined that the universe is expanding because he found that distant galaxies were being redshifted. So redshift is a Doppler effect. A Doppler effect stretches wavelengths of radiation from receding objects towards the red end of the spectrum. So if you have a look at the spectrum, we have red at one end and violet at the other end. So with a receding object, the wavelengths are stretched, and red has got our longest wavelength. So as the wavelengths get stretched, all of the colours move towards the red end of the spectrum. So this is why we call it a red shift. If an object is approaching us, it'll actually be blue shifted. So the waves are compressed, the frequency goes up, so all of the colours get pushed towards the blue or the violet end of the spectrum. And he also found that the farther the galaxy is, the greater the redshift and the faster it is receding. Now, redshift itself is measured as a fraction and is denoted by the letter Z, lowercase z. So, for example, if we have Z equals 0.05, this means that the wavelength is being shifted by 5%. If we have a Z equals 1, this means the wavelength is shifted by 100%. And we've found that some early galaxies have got redshifts exceeding 14. So they're pretty well pushed right out of the visible spectrum altogether and into the infrared. Now, the only galaxies we've found that experience blue shifts, which means that they're moving towards us, are several in the local group, because the local group of galaxies is gravitationally bound. So they're not subjected to the expansion of the universe. So some of those, and also in the neighbouring Virgo cluster, are actually moving towards us. So if you have a look at the spectrum of the sun, the absorption lines, if you take a spectrum of the sun, you'll see these black lines appearing within it. So these are absorption lines in the spectrum, and these are caused by gases in the sun's atmosphere absorbing certain bands of light, and so we get this like a fingerprint. And by looking at this fingerprint, we can determine which elements are present in a star's atmosphere. And most stars have got the same, because all stars are made up of hydrogen and helium gas, and with some oxygen and nitrogen thrown in. Most stars give the same pattern of lines. So by looking at the lines from a supercluster of galaxies a billion light years away, we can see all these lines are moved towards. There's the same pattern of lines but they've been moved towards the red end of the spectrum. So by looking at this displacement between that line and this line, by looking at that displacement, we can work out the velocity of the receding galaxies and also the distance. And that brings us to the Hubble-Lemaitre law. So Hubble, he sort of determined, using this equation, velocity equals h0, which is the Hubble constant, multiplied by distance. So by using this relationship, if you can work out the velocity that the galaxy is receding from us, you can work out its distance. The actual Hubble constant is a little bit rubbery. It's taken about 100 years to try and pin it down. And we've used various methods from Cepheid variables to the WMAP probes and also gravitational wave data, and appears to be around about a value of 75. It's called a constant, but it is not actually a constant, because as the universe expands, the actual Hubble constant changes as well. But in a human lifetime, it's pretty well fixed at about that value. And its units are kilometres per second per megaparsec. So for every megaparsec that we move out into space, we get 75 kilometres per second faster. That's what it sort of means. So by plugging that in there, and if you look at this table here with velocity, which is in kilometres per second, you'll notice that the top value is the speed of light, 300,000 kilometres per second. So you can see that when we're looking out, 4,000 megaparsecs is pretty well at the edge of the observable universe. So as objects are approaching that distance, they actually appear to be receding close to the speed of light. It's a little bit of a misnomer. They're not actually travelling that fast, but the universe is expanding and carrying these objects away from us, and that's how they appear to be travelling. Now, the Big Bang. So current theory suggests that time, space and matter were all created in a single event about 13.8 billion years ago. It was first proposed by Georges Lemaitre. He's come up quite a few times in this talk. In 1927. He called it the primeval atom, or the cosmic egg. The actual phrase Big Bang was coined by Fred Hoyle in 1949 during a BBC radio broadcast. He didn't actually support the Big Bang theory. He supported the steady state universe theory. Now, the steady state universe theory, it's not actually a static universe. He realised that the universe was expanding. He just believed that it's always been expanding, and matter has always been created to fill in the void as everything is receding. So that's sort of what the steady state theory is. And he believes that the universe was always there. So he coined the phrase Big Bang in a derogatory way, and was actually rather dismayed when it caught on. Now, one of the great pieces of evidence we have for the Big Bang is the cosmic background radiation. Now, this is the radiation that permeates all of space. it doesn't matter where you look, you'll see this cosmic background radiation. And it appears to be the remnant of the Big Bang fireball. So when the Big Bang went off, the universe was extremely hot. And as it expanded, it cooled down. So as it cooled down and expanded, the wavelengths were stretched so that the radiation is now in the microwave band. And it represents a temperature of 2.7 Kelvin, or 2.7 degrees above absolute zero. And we've sent up several probes to map this. Firstly was the COBE probe, then the WMAP, and finally the Planck surveyor. Each of these satellites was more sensitive than the one before it. So you can see in the diagram here, the top one is WMAP, and then this one's the Planck. And you can actually see the pattern is the same, but it's just a lot more resolution, better resolution with the Planck satellite data. So this is like a full all-sky image. And so the red areas are the warm spots, and the blue areas are the cooler spots in the radiation, roughly around this 2.7 degrees Kelvin. But it's extremely, the variations are very, very small. You can see here between the coldest and warmest is only about 0.4 millikelvin. So it's very, very smooth, but there is some fluctuation in it, and we believe that these fluctuations in the early universe is what caused the original clumping of matter and the creation of galaxies. If it was completely smooth and there were no variations at all, we probably wouldn't have had the universe we have today. Okay, now I'm just going to talk about the forces of nature and how they were created during the Big Bang. So the one most people are familiar with is gravity, which is the force of attraction between masses. Now this is an extremely weak force when you compare it to the other forces, but it's felt across the universe. Now, when I say it's weak, you probably dispute that if you fell off the roof of a house, but compared to electromagnetism, it is 10 with 19 zeros after it, times weaker than electromagnetism. So you can get a fridge magnet, and you can pick up a pin off the table against the entire gravitational field of the Earth. That sort of just gives you some idea how weak gravity is. And of course, Einstein believes that gravity isn't a force at all. He believes that gravity is just mass distorting space-time. So everything travels in a straight line, but if space-time itself is curved, which is caused by a massive object, that is how we feel gravity. But for this talk, we'll stick with it as a force. All these forces have got a carrier particle associated with it, which actually mediates that force. In the case of gravity, the force carrier particle is a hypothetical one because it's never been detected. It's called the graviton, and one of the reasons it probably hasn't been detected is because gravity is such a weak force. The other one that most people are familiar with is electromagnetism. So this is a combination of electric and magnetic fields. They're 90 degrees displaced from each other. So we have like poles, charges repel, unlike charges attract, and light is an example of an electromagnetic wave. It's a very strong force, and it's felt across the universe. And the force carrier particle for electromagnetism is the photon, which you're probably familiar with. And the photon can be considered a particle or a wave, just depending on how you look at it and how you measure it. The next one we have is the strong force. Now this is 130 times stronger than electromagnetism. And it's the force that binds atomic nuclei together, because in an atomic nucleus, It's full of protons. And all the protons are positively charged. And all they want to do is repel each other, and if there wasn't any strong force, all nuclei would disintegrate because of all the positively charged protons repelling each other. So the strong force, by necessity, has to be stronger than electromagnetism to overcome the repulsion between the protons. And this is why very massive atoms, like uranium and that, they've got so many protons in the nucleus that they're starting to overcome the strong force, and that's why they're unstable and tend to disintegrate. The strong force is also the force that holds quarks together in a proton and a neutron. They're not fundamental particles, they're composed of quarks, whatever you call them, and the strong force is what binds that together as well. The force carrier particle for the strong force is called the gluon, for obvious reasons. It glues the protons together. The last one's a little bit obscure. It's the weak nuclear force, and it's responsible for particle decay. And it has two carrier particles, the W and the Z boson. Now, both the strong force and the weak force are extremely short-range forces. They only operate within the nucleus of an atom. They don't have any influence beyond that. So how does this tie in with the Big Bang? Well, it appears that when the Big Bang occurred, there was only one force. It was called the superforce, which was a combination of all the forces. And then a very, very short time after the Big Bang, like 10 to the minus 43 seconds after, gravity emerged as a force from the superforce. What we have is the gut force, or grand unified theory force. Then a short time later, 10 to the minus 35 seconds after the Big Bang, the strong nuclear force emerged as a separate force. And then 10 to the minus 11 seconds after the Big Bang, the weak and electromagnetic forces separated as well, and that's how the four forces emerged from the Big Bang. Well, that's what we believe anyway. Don't ask me how they know that. So we have a bit of a timeline here. So less than 10 to the minus 43 seconds, this is actually what's called Planck time. Planck time is the smallest unit of time that we can measure. And any earlier than that, the laws of physics don't apply anymore. So at 10 to the minus 3 seconds, the temperature of the universe, at this point the universe is about the size of a grapefruit. The temperature is about 10 to the power 32 Kelvin. And it's at this time, Planck time, that's when gravity emerged as a force. Then 10 to the minus 35, that's when the strong force emerged. And just in that very short space of time, the temperature of the universe has cooled from 10 to the 32 to 10 to the 27 Kelvin. And so about this time, the inflation begins. So the original theories with the Big Bang had a lot of problems with it. The universe was much bigger than it should be if it was just a linear expansion from the Big Bang. So what we believe happened is a very short time after the Big Bang, like 10 to the minus 35 seconds, the universe underwent a very rapid and very great expansion called inflation. So it went from basically the size of a grapefruit to cosmological size in less than a second. It just sort of went, boom, really big. And when they did that, we got the theory then worked, and we got the universe that we see today. So 10 to the minus 33, that's when electromagnetic and weak forces separated out. At 1 microsecond after the Big Bang, the universe was cooled to 10 to the 13 Kelvin, and this is where the quarks form protons and neutrons, and matter-antimatter annihilation begins. So when the Big Bang occurred, there was roughly the same amount of matter and antimatter produced in the explosion, if you call it that. Now, matter and antimatter do not like to coexist. If they come in contact with each other, they annihilate. So we end up with a lot of annihilation going on, and we believe that there was a slightly more matter than antimatter created in the Big Bang. So after all this annihilation was done with, there was a small excess of matter left over, and that matter became all the matter in the universe. So there must have been a lot of matter produced in the Big Bang to start with. Well, this is how we believe that why there is so little antimatter in the universe. Then 10 to the minus 4 seconds, electrons and neutrinos form. Then 10 seconds after the Big Bang, the universe had cooled to about 1 billion degrees, and it was cool enough then for hydrogen and helium nuclei to form, with a tiny, tiny little bit of lithium. So at greater than 1 minute, we've cooled down to 10 to the 8, we come to the era of radiation. So all of the matter that's been created is highly ionised because of the temperature. So we don't have atoms, we only have nuclei and a sea of electrons. So everything's ionised, and because of this, the universe is opaque. So radiation can't penetrate the dense hot matter. And it's not until about 100 million years after the Big Bang, where the temperatures cool down to about 100 degrees. This is the era of matter. So this is when the universe becomes transparent and stars begin to form. So this is a bit like I guess a barrier to observation. We can't look back to any earlier than this point here, because the universe is opaque and we can't see any further than that. We all we see is basically the cosmic background radiation pattern, and that's it. So we've got some various models of how the universe evolves. So here we have the time of the Big Bang, and we have the size of the universe and time. So we have this term omega 0, which is the density ratio. So this is how much matter there is in the volume of the universe. So if there's enough matter where the density ratio equals 1, we end up with what's called a flat universe. So it initially starts to expand, and then gravity tries to slow the expansion down, and there's just enough matter for it to sort of go to a flat line. So this is the flat universe. If omega 0 is greater than 1, so there's more matter than that which could create a flat universe, then gravity will eventually slow the expansion down, and all the matter then will start to pull back in again, and we'll end up with a big crunch as the universe collapses back in on itself. If omega 0 is less than 1, this will mean that the universe will expand forever, and it'll end up as a cold death as all the stars burn out eventually. But it appears that none of these three are actually what's happening. It appears to be the black line, where it's an accelerating universe. So the universe started to expand, and then about 7 billion years ago, it started to undergo an acceleration in the expansion. And this is where the cosmological constant comes back into it. So it looks like Einstein was actually right all along. We need a cosmological constant to account for this accelerating expansion of the universe. So now we move on to dark matter. So it appears that the universe contains 5 times more dark matter than observable normal matter. So when we look at a galaxy, we can see the stars and we can see nebula, but there appears to be about 5 times more matter than that in a galaxy to account for its rotation. So this is the galaxy M33, and if we look at the matter that we can see, this is the curve that we would expect to get. So this is velocity of the stars and their radius out from the centre. So you can expect as we move out from the centre of the galaxy, they would slow down. It's a bit like in the solar system that the planets further out revolve slower than the planets close to the sun. So that's what we'd expect. But when we observe the speed of stars in the galaxy, and any spiral galaxy, we notice that the stars further out are actually moving a lot faster than the ones close in. Now, if all the matter was what we can see, then these speeds would mean that the galaxy would fly apart. So there needs to be a lot more mass there to create a lot more gravity to hold the stars in place because of at these high speeds at the edges of the disk. Right, so what is dark matter? So there's a few suggestions or a few theories, and we really don't know what it is. We have machos, which are massive compact halo objects. So these are normal matter objects, but are invisible. For instance, brown dwarfs, black holes, that sort of thing. And then we have WIMPs, which are weakly interactive massive particles. So this is non-baryonic matter that rarely interacts with normal matter. So these are like subatomic particles that we haven't detected yet, but they have a lot of mass, and they only interact with normal matter through gravity. Then we have neutrinos. Now there are more neutrinos than any other particle in the universe. The universe is saturated with neutrinos. Every second there's about 1 trillion of them going through your body from the sun. But they have very, very tiny masses. But because there are a lot of them, there's a possibility that perhaps that's contributing to dark matter. And there's also neutralinos, which are a hypothetical particle, but a popular form of WIMP to contribute to dark matter. And if you have a look at this image here, we have here a gravitational lensing. So we have a cluster of foreground galaxies, and their gravity is bending the light from background galaxies to form these arcs. And the only way we can get this pattern of lensing is if there was a lot more matter within these clusters. So they've actually put the dark matter into the image in blue, so that we haven't actually photographed that. They've added it into the photograph to show where the dark matter would be to create the gravitational lensing that we can see. Then we come to dark energy. So, as I said earlier, the current model for the universe is the open model. So not only is there insufficient mass to cause a collapse, the expansion is actually accelerating. And this was determined back in the 90s when they were studying the distant type 1a supernova. So type 1a supernova often uses standard candles, because every time a type 1a supernova goes off, all of them are pretty much the same brightness, intrinsic brightness, because the mechanism to create a type 1 supernova is almost identical between any other type 1a supernova. So we use them as standard candles. So we're looking at how bright they are. We can work out the distance that their host galaxy is. And they noticed that, that they were fainter than they should be without an accelerating universe. So this dark energy appears to be an anti-gravitational force. So if we have a look at this diagram here, we have the Big Bang here, and then we had inflation, so it got big really, really quick. And then we had sort of a linear expansion till about 7 billion years ago, and then it started to accelerate. And this is what dark energy has done. It's accelerating the expansion of the universe. So there we are here, this is the present here. So have a look up the makeup of the universe, like a pie chart. This is the mass energy of the universe, basically, because mass and energy are equivalent, okay? So we find that 4% of it is normal matter, like what the Earth's made of and we're made of. 21% of it is dark matter, which we don't know what it is, and 75% of it is dark energy, which we don't know what it is. So we don't know a lot, really, do we? So, current model of the universe, it's a little bit like the other diagram. We have the Big Bang here, rapid inflation. So when we look back in time, this is the afterglow pattern we see with the cosmic background radiation, which is about 400,000 years after the Big Bang, and we can't see beyond that point because of the universe is opaque. Then we had a period called the Dark Ages. This is because even though the universe was transparent, there were no stars born yet, so everything was dark. So about 400 million years after the Big Bang, the first stars started to form, and from that point onwards, we see the normal evolution of the universe. And then about 7 billion years, you can see here the expansion starting to accelerate. So the future of the universe. So if dark energy continues to accelerate the expansion of the universe, then in about 20 billion years, all bound systems will disintegrate. So what that means is the universe will be expanding so rapidly that the space, like the space between the stars and the planets, will be changing at a rapid rate, so that the planets will be ripped out of the orbit of stars, because the space between the planet and the stars is expanding so fast. So initially we'll see galaxies start to be torn apart, then solar systems, followed by stars and planets, and finally atoms themselves will start to disintegrate, because the space inside an atom will be accelerating so fast with the expansion of the universe. So this is called the Big Rip, as everything just flies apart. But we do have alternate ends to the universe. So if the universe continues to expand at the current rate, in 1 trillion years, the last red dwarf star will burn out, because they're the longest, they're the stars that live the longest. In 10 to the 20 years, black holes will begin to evaporate due to Hawking radiation. 10 to the 40 years, protons start to decay into photons. 10 to the 60 years, almost all matter has decayed into photons, and the average distance between each photon will be 1 light year. Something to look forward to. Any questions? Hi, Peter. Yes?
You know that first
The redshift, yeah.
the colour you had there was
Got to get right at the start now, isn't it? This, that one?
No,
That one?
yeah.
Yep. Sorry, what? So what was the question again?
The colours themselves
Yeah, it just means that,
it's not an actual spectrum, is it?
no, it's just a representation. But you can see here that that line there from the sun, in a distant galaxy, it appears over here.
Yeah, but the red with the boundary.
Yeah, that's fixed. So we're just looking at the way that the lines are shifted. Yeah, we're just using that as your reference, right? So yeah, the spectrum is your reference, but the lines have shifted towards the red in a distant galaxies. Yeah. Anyone going to ask another question? Okay, well, thank you very much.